William I don't know how you pronounce how do you pronounce your last name? Taggart. Thank you. William M. Taggart IV has been a professional engineer for 34 years, working on major projects in deep water oil and gas, shale oil, copper mining, and refineries. Recognized as subject matter expert for process controls and process safety, and active on industry committees that define the standards and requirements for process safety on offshore platform and subsea wells. Now focused on large-scale energy storage, as well as serving as a consultant to the oil and gas industry. Morning.
Good morning. Thank you very much. So I'd like to talk to you all about an opportunity for electrical energy storage. So our electricity use fluctuates with demand. So as you can see, this is Texas in July. At night, you have low energy electricity use. During the day, when all the air conditioning units are running, you get very high use. And it's a nice sinusoidal curve that you get. Well, behind the scenes, it looks a little different. You've got your nuclear power plants running at a constant power. There. You've got a little bit of fluctuation on your coal. Your solar and your wind is weather dependent, so they're varying a lot. There's solar, there's your wind. And you've got the poor natural gas power generators making up the difference. They are constantly changing their power output to match with what the other guys are producing and then to match up with the demand. Now, in winter, in February of this year, it was a little different. The sinusoidal curve is gone. It's now dependent on what the temperature is in Texas. And it's semi-steady, kinda. But behind the scenes, it's even crazier. So right here, we've got a cold front coming through with a lot of wind. We are 50% wind power at this point in Texas. But here, when the wind drops off, you can see the natural gas power suppliers have to immediately get online and come up and match the demand. So there's a lot going on there. So when you look at the United States electrical grid, we've got 6 major electrical producers. Of those, natural gas, coal, and hydro can adjust to demand. With natural gas, the storage that we put in salt domes and in depleted reservoirs is our energy storage for that natural gas system. For a coal power plant, there's usually a big pile of coal next to it. That's the energy storage. And for hydroelectric, they open and close the gates to turn the turbines more or less. They can adjust to demand. But then you've got nuclear that can't adjust to demand. And if you want to know why, look me up afterwards. I'll explain the whole thing about thermal momentum and why a nuclear power plant does not like to change its output. But then you've got solar and wind. And these are weather dependent. So as you see, they're almost 13% of America's energy supply, but they change and they vary. So as a result, as that percentage increases, you need more energy storage. But at the moment, the U.S. consumes almost 13,000 gigawatt hours a day, and we've only got about 500 plus gigawatt hours of electrical storage. And the challenge here is that's usually on a 30-hour storage. There's really only about 250 gigawatt hours per day that you can use for storage. So about 2%. And when you look at Texas, it's even worse. Now your wind and solar is over 28% of your energy supply. That was for last year in 2021. The first 3 months of this year, we've been 34% solar and wind. But we've got less than 0.25% of energy storage as presently on the grid. And of that 3 gigawatt hours, it's mainly lithium-ion batteries. And the Department of Energy recognizes this. They've formed what they call the Energy Storage Grand Challenge. And the point of the Energy Storage Grand Challenge is to find and commercialize new forms of long-duration energy storage to resolve this. And DOE estimates that we need about 1,000 gigawatt hours of energy storage to support a larger renewable economy. At the moment, we've only got 26 gigawatt hours of energy storage, compared to over 1,124 gigawatts of power generation. And of that, 23 gigawatts is pumped storage hydroelectric. And Department of Energy only estimates that we can probably add about 52 gigawatts to that system. And most of the new installations we're looking at are batteries right now. So let's discuss what are our energy storage options at the moment. You've got lithium-ion batteries. This is presently what's being developed in most places and in most locations. In Texas, we've got 1.6 gigawatts of installed storage, and there's another 5 gigawatts under development. It's about 86 to 88% efficient, and you've got about a 3 to 6 years life for the batteries, which is cycle driven. So every time you charge the battery and discharge it, that's a cycle. And lithium-ion batteries are cycle limited. You should know that from your phone, because of the way the phone behaves. The problem is world lithium production is about 90,000 tons per year in last year. And as we change the US auto fleet over to electric vehicles, that it's going to need about 3 million tons of lithium for that, just for that purpose. Now, one of the other problems is the cost of lithium. This is what the cost of lithium has done in the last year. This is a Chinese market that's in renminbi per ton. And in the last year, it has gone up by a factor of 5. This is not due to the Russian-Ukraine war. Russia and Ukraine do not make any lithium. In fact, 3 countries make the bulk of the lithium: Australia, Chile, and China. That's 95% of the world lithium production right there. And that price actually this morning was 462,000 renminbi per ton right now. The second option we have for batteries is what's called redox flow. This is a new technology. There's very few installations. The idea is you have 2 large tanks of electrolyte and you flow them through a cell, and flowing through that cell is where you charge or discharge the battery. As a result, it has a very large footprint. You will never put this in a car or a phone. It is only for grid use. And it's got about 68 to 78% efficiency. The other option is compressed air energy storage, something this group has talked about. At present moment, there are only 2 existing large-scale plants, one in Alabama and one in Germany. The Alabama plant is 110 megawatts. Now, it's only 52% efficient. The reason is you have to compress the air. Once you compress the air, it gets hot. Once it's hot, you have to get rid of the heat. Then you store it. When you want to get the electricity back, you bring it out of the storage, you expand it. As it expands, it cools. In fact, it gets very, very cold. The plant in Alabama uses supplemental natural gas firing to actually heat the compressed air up as part of the expansion process. And then you get the electricity. So right now, that plant in Alabama is not very green. It depends on natural gas for its supplemental heating at this time. There's a lot of development going on about how to store the heat during compression and then reuse that heat during expansion to make the system more efficient and more green. None of those installations have been built yet. And now hydrogen. We have a lot of papers on hydrogen coming up because it's the darling right now. But the thing is, there is no large-scale developments right now. There is no large-scale infrastructure in place at this time. And one of the reasons is that the Department of Energy's own reports say the efficiency is about 35%. If you start from electricity, use electrolysis, compression, storage, expansion, and then back to electricity, you are 35% efficient. And that brings us to pumped storage hydroelectric. This is the workhorse of energy storage, not only in America, but worldwide. It is 90% of the worldwide projects. In America, it's 85%. And from a storage standpoint, it's 95% of our electricity energy storage in America. But as I said earlier, there's 23 gigawatts installed, and the DOE figures they can maybe add another 52 gigawatts. It's 80% efficient. It's one of the more efficient systems on the market today. And the operating life is long. It lasts for more than 40 years. There are European installations that have been operating for over 100 years. And this is where our pumped storage hydroelectric facilities are located. The blue dots show where they're at. The red dots are where they're planned, and the light blue dot, light greenish dots are where they're indicated they are planning to build new units. And when I mention that 52 gigawatt, they are in these areas. Mountainous areas, because the way pumped storage works is you have 2 reservoirs on the side of a mountain. When you want to store electricity, you pump water from the lower reservoir to the upper. When you want to recover it, you let that water flow back through a hydroelectric turbine to generate electricity. Texas, Louisiana, Mississippi have no existing or planned pumped storage hydroelectric facilities because the land is simply too flat. We're never going to see them in the Gulf Coast region. So what are you going to do about energy storage in the Gulf Coast? Pumped storage hydroelectric needs specific geographic locations where you can have that high elevation difference between your water storage reservoirs. Compressed air is inefficient, and hydrogen is even more inefficient. And batteries have limited lives, and their costs are going to start going up as you start to convert more vehicles to electric. So what are our options for the Gulf Coast? And this is where I'm thinking. This is underground pumped storage hydroelectric, where you take the reservoirs, that upper and lower reservoirs from pumped storage hydroelectric, and you relocate them into a salt dome cavern. You then use compressed air to pressurize the caverns, raising the surface pressures and creating the void spaces within the caverns that you move the fluids between. Now, I don't need to talk to y'all about salt dome caverns. This is usually the part of the presentation where I have to explain to people that salt dome caverns really do exist. But I want to also point out to you that this is the area that you should be familiar with where salt dome caverns are. And the thing to understand here is 25 million people live within this region. And based on DOE's estimates, they need 75,000 megawatts of energy storage. Another thing to point out is that as we develop offshore wind farms, there are near-shore salt dome caverns that could be developed in conjunction with them to provide energy storage for those offshore wind farms. This is not a new idea. There were patents in the 1970s and 1980s where people were already discussing this idea. Now, some of them did not pressurize the caverns, and as a result, they put the pump house down in the salt dome cavern. In other cases, they used solution mine tunnels to move air and fluid around. None of these were ever built. So how do we set this thing up? You make two caverns full of brine. You add compressed air to both. The compressed air raises the surface pressure of the brine strings. For the lower cavern, it raises it to about 60 psi, about 4 bar. For the upper cavern, it raises it to about 640 psig. What's that, about 42 bar? I'm having trouble doing that in my head. For the pump turbine that's on the surface, this looks exactly like conventional pumped storage hydroelectric. So when you want to store electricity, you pump brine from the lower cavern to the upper cavern. At the same time, compressed air is freely flowing from the upper to the lower to replace, as you're moving the spaces around, essentially. And it's flowing through the well bores. So the brine flows through the well bore, the compressed air flows through the annuluses. When you want to recover that electricity, you do the opposite. You let the brine flow through the turbine on the surface down to the lower cavern. At the same time, the compressed air is flowing the opposite way. Oh, I forgot to mention one thing. So to store 50 megawatt hours of electricity, you have to move 290,000 barrels of brine. You've got to move a lot of fluid. Keep that in mind. That point we'll come back to discuss in a moment. Oh, and you're moving at 1,250 feet in elevation as well. So what we want to do, we want to build an alpha demonstration unit. We want to take two existing salt dome caverns, about 200-foot diameter, over 1,500 feet in height. So if you have two existing salt dome caverns that are very close together and they're not doing anything for you, please contact me. I'd like to know. So what we're going to do is we're going to use the existing wells. We're not going to do anything to the caverns. We're going to receive them and we're going to turn them back to you as is, or as close to as is as we can do. And we'll fill them with compressed air. Can I have the microphone? Keep moving. Hello? So what we're going to do, we're going to pump in compressed air. We're going to let brine come out of this, what we're going to call the upper reservoir, take the brine out and fill this with compressed air. Then we'll fill this with compressed air to this level. So now you've got two different levels. Now because we're using the existing wells and we're not going to do anything, we will probably not get the energy storage targets and the capacity that we want. We're just going to have to, but this is the cheap way to test out and make sure that this technology works. So the idea is and the compressed gas pressure would probably be between 1,500 and 2,500 psig, depending on the depth underground and the casing chute pressure limitation. For existing caverns, the casing chute pressure limitation is probably going to limit us to what we can do here because these caverns are not built for energy storage. But it lets us test out the technology and check it out and make sure we don't have any unwarranted, unforeseen issues that can pop up. So the idea is we would run this for about a year. Now, let me point out, this piece here is not being used, and this piece here is just not being used, and it's full of compressed air. And by the way, compressed air does not come cheap. So that's extra money right there. So after a year, we would build the beta unit. The point of the beta unit is actually to achieve 80% efficiency and to achieve the energy storage targets that we have. So we would create 2 new caverns that are 200 feet in diameter, and each cavern is only 250 feet in height. We use multiple wells to penetrate into the caverns. Remember, we were talking about 290,000 barrels of fluid that we have to move for a 50 megawatt of energy storage. As a result, you need large well bores and you need multiple well bores to do it. Again, we add compressed air to get the system to work. This design of 2 200-foot caverns couldn't be the first phase to a commercial unit. So this is a 5 megawatt capacity. That's 5 megawatts. It can put instantaneous power on the network, and it stores up to 30 hours of electricity, so it has 150 megawatt hours of energy storage. And when I take multiple caverns like that and link them together, I get this situation. This is 25 lower level caverns and 25 upper level caverns. 5 uppers and 5 lowers are ganged together in headers. They tie to a 25 megawatt pump turbine. There are 5 of them. You now have a 125 megawatt power installation on 90 acres of salt dome. The capital cost is in line with other large-scale energy storage systems as well. The surface area, we use less than 10% of the surface area. You could have grazing, solar panels, wind turbines. You can use the surface area for other applications. This would be what the plan view would look like. So you've got blue caverns in the upper level, green caverns in the lower level, and the black boxes are the powerhouses on the surface. It's a 200-foot caverns with 200 foot of separation at each level and a 100-foot border on the area, on the perimeter. These are assumptions I've made. One of the next steps is going to be to get cavern engineers to look at this and make sure these assumptions work and are valid. When I remove the lower level caverns, you can see that the upper level caverns and the 200-foot spacing is in place. Okay, so for any new technology like this, there are challenges. So what are they? Well, the first one is obvious. We're choosing to use saturated brine because it's the most economical working fluid. As a result, that gives us challenges around material. So most pumped storage hydroelectric facilities use water. There's a few that are using seawater. But because we're using a saturated brine, we're going to look at the metallurgy very carefully. We're looking at austenitic and duplex stainless steels at the moment. The wells in the dome are going to be exposed to compressed air and brine. We're worried about that. Existing cavern operators, we would love to have conversations with you and find out what your experience has been with different metallurgies, because we're looking to find the best system that will give us corrosion resistance versus cost. We're looking at a 40 to 50 year design life here. The other thing about saturated brine is it has the potential to precipitate out salt in the equipment. The goal here is going to be to maintain the brine temperature to match the cavern temperature as closely as possible to prevent any precipitation of salt in the surface piping or the surface equipment. We'll be insulating the pipes. We may add some supplemental heat. That's something that's being looked at the moment. Inspection and monitoring during the alpha and beta demonstration units is going to be critical for us to confirm how we keep salt from depositing in the top side. The other thing, the concern there is if salt is being deposited in the surface piping and the surface equipment, then you've got a subsaturated fluid going back into the cavern that could leach additional salt off the walls. That would also interfere with our 50-year design life. One of the other challenges is cost. So the DOE target is $50 per megawatt hour. Now that's $50 between when you buy the electricity that you're storing at night when electricity is not in demand, versus the price you pay when you release that electricity back to the grid when there's high demand. The DOE is targeting a $50 difference. So Texas in 2020, that averaged $22 per megawatt hour. But in 2021, and this is only if you exclude the February freeze that was absolutely insane, you have about $39 per megawatt hour. And for the first 3 months of this year, it's run at $48 per megawatt hour. So the $50 target that DOE is aiming at is now starting to be seen in the Texas market. It's come up to that level. Now the challenge is underground pumped storage hydro needs more than $50 per megawatt hour to be profitable. But the other thing in our favor is all the other large-scale energy storage systems have the same issue. They all need more than $50 per megawatt hour. The whole point of the Department of Energy challenge is to try and get all the large-scale systems down to $50 per megawatt hour. But we do have an advantage in that area. So wells and drilling are 70% of the estimated cost in the commercial units. Shale oil companies were able to get their drilling costs down by working with drillers and with suppliers. If we can see a similar cost reduction in this system, we could get down to the $50 per megawatt hour price point. So what's our path forward? As I said, if you have two existing salt dome caverns that are in close proximity to each other, I want to talk to you, because that's what we're looking to do next, is to build the alpha demonstration unit. We're looking for private investors and electrical grid operators to generate capital investment. We're working with pump turbine suppliers on possible metallurgy and confirming cost and delivery schedule, and we're working with drilling companies to confirm size and cost of the wells needed for the alpha and beta commercial units. Now, hydrogen, compressed air, and underground pumped storage hydro all want salt dome caverns. So why pick underground pumped storage hydro? First of all, it's using the proven technology of pumped storage hydroelectric that is the workhorse of present energy storage. Second, its efficiency is 80%. Compressed air and hydrogen are 52% or less. And we expect underground pumped storage hydro to be very reliable. It has very few moving parts, only the pump turbine and the valves. And existing pumped storage hydro systems have run reliably for 40 years. But this isn't a choice between. There's enough salt domes to allow all three technologies to be implemented. And each technology provides a different function. Underground pumped storage hydro moves electricity within a 24 to 72-hour window. Compressed air could be focused on larger time bases, storing energy for seasons and months. And hydrogen gives you a large-scale storage of a dispatchable fuel that could be used in trucking, agricultural, and remote locations. These are three separate tools in the toolbox, and we really need all three to make the system work. So thank you very much for listening, and if anyone is interested, please contact me. And I'm open for questions.
Thanks for that excellent presentation. I'd never thought about pumped hydro underground, and it really eliminates one of the big issues the public has with surface pumped hydro, which is the surface use. And so I really like putting this underground. Could you talk a little bit about, you talked about moving a lot of brine. How does that compare to the amount of water that would be moved in a traditional pump?
Same thing.
Same volume?
So the whole point with energy storage is and this is what's called a gravity system, because you're using gravity as your energy storage mechanism. So you're taking a cubic meter of water, of brine, and you're moving it up 1,250 feet, and that stores a kilowatt hour of electricity. And pumped storage hydro works the same way. You're taking a cubic meter of water and you're moving it up by different elevations. So the higher the elevation, the more energy storage you get. And that actually comes back to a point which I should have made during the presentation. The casing chute pressure is very important. The higher the compressed air pressure I can use, the higher the elevation difference I can get between the two reservoirs underground, the more energy dense the brine is when I move it between the two reservoirs. So there's a balancing act there. And in the commercial slide of the commercial unit that I showed, the upper caverns were at 3,200 foot elevation and the lowers were at 4,450 foot elevation. And that was to allow me to use a higher compressed air pressure to get the difference I needed.
Excellent. You answered my next question too, so thanks.
Okay. Lady in the back.
Hi, thank you. I am a geologist, so I have a question. Geologically, have you thought about what the implications of that much flux and that many caverns all together, and have you just looked at any of the geologic conditions?
So The pressure in the caverns is constant. It fluctuates by about 25 psig as I move brine back and forth. So once the caverns are established, there's very little pressure change, and if we can solve the temperature problem, there'll be no temperature change as well. So we think we have a stable unit, but we've got to get farther into the engineering and hopefully the demonstration units to confirm that. And for one reason why we're having pressure differences, the pressure changes because as the compressed air moves from one cavern to the other, there's actually, we start with the same compressed air pressure at the surface, but as you get to the upper cavern, it's one pressure, and as you get deeper into the lower cavern, it's a slightly higher pressure. And as you move that more pressurized air to the upper cavern, it causes the overall system pressure to rise slightly. It's about a 25 psig change, or about less than 2 bar change that we're seeing.
Two questions around efficiency. Is each cavern required to have a dual entry?
So
from a CapEx perspective,
okay, hold on, here's the fun part. So the way I have it depicted is those are two 24-inch brine strings with 30-inch and 36-inch casings in the depiction that you saw. Yeah. Don't panic. They've drilled wells that big. Now, you can have two 24 inches, or you can have 6 16-inch brine strings, or you can have 12 12-inch brine strings. The next thing we're going to do is try to figure out what is the most economical and what's technically feasible. But because, and it gets back to your question, you pointed out with efficiency, pressure loss in the well bores is lost electricity. So I'm using these big well strings and multiple well strings to try and minimize my pressure drop to allow me to reach that 80% efficiency. Did I answer you?
Yes, and also have you considered incorporating case trains at surface when the air is moving? So, generating electricity.
No, because so you could try and put in some sort of turbine that the compressed air would push and move and while it's flowing, but that just adds more pressure restriction, which means you're losing electricity on the brine side. So you want to minimize pressure drop in the system because where you're storing the energy is by moving the brine up and back. That's where you're getting your main energy storage. Yvonne over here.
Yeah, trying to find a way to get there.
I always worry about running out of time. And these are bifocals. That screen was giving me fits.
Just one quick question. What would be the flow rates you would normally work with on any peak day that you have to deliver?
So the flow rate is for the beta demonstration unit, the 5 megawatt unit. That's 20,000 gallons per minute flow rate.
That's quite high.
Well, that's the challenge because you're moving 290,000 barrels in a 10-hour window.
Okay, we take a last question.
Yep. This guy over here, he's been quite patient.
Thank you. Actually, it was about the same question. When you've got basically liquid caverns and you consider 24 hours to 72 hours cycles. So in our industry, liquid caverns are like never emptied in 24 hours. Oh, because it's huge flow rate. So this is one of your challenge, I think.
Oh yes, and that's why we've got the multiple well bores. And really, so the cavern system, the commercial system is designed for 30 hours of energy storage. Practically, the way pumped storage hydroelectric works is you store about 8 to 10 hours at night, and then you unload that 8 to 10 hours during the day. So that's how it'll practically run, but we've got 30 hours of potential storage. So if you had a hurricane or an event, we can go deeper into the gravity battery, as it were, to keep supplying energy. The other thing is, think about this teamed up with a wind turbine system where they have 10 hours of amazing wind performance where you can bank all that extra electricity and then supply it over the next 30 hours when you don't have any wind at all. We're trying to pair this up around that ideas of having, we're planning for 30 hours of energy storage, but really we're using 8 to 10. Anything else? Gentleman in the back.
Nope.
Oh, was that the last one, Yvonne?
I was supposed to be, but
Oh, I'm
okay,
sorry.
I'll make an exception.
He can grab me in the hallway.
So this is the extremely very late last one.
We're on time.
Niels, WSP. So with your friction losses, obviously that's converted to heat, and this is over underground. So do you think over time, if you run this system hard, you will heat up the rock and it will heat up the fluids, and eventually would have to cool it at surface, or any thoughts on that?
So the thermodynamic study is the next one around. The heat loss, so it's hard to explain. Now I'm going to go way over time. What's happening is as the compressed air goes from one cavern up to the surface, it's decreasing in pressure and it cools actually, and it's cooling the brine coming down into the cavern. Whereas the compressed air is coming down on the other side, it's actually heating up because of compression, and it's actually heating the brine going up. So there is actually that going on as well. The friction losses and the friction in the piping is very minor heat, so you're going to be losing a little bit of heat off into the formation. That's something that we need to look at. The thermodynamic study is the next thing we're going to get into. And we really need to have the alpha unit to run to really see what happens here with a thermal management idea. All right. If anyone has any other questions, please give me a shout.
Thanks a lot.